Okay, hello everyone, and welcome back to another one of these review of proof techniques videos. So in this video, we'll be looking at the proof by contradiction technique. So in a proof by contradiction, you assume that the result of the statement you're trying to prove is false. So for instance, in the statement, if P then Q, you assume the result, so assume Q is false. Or, for instance, in the statement just Q, so if you're just stating something like the square root of 2 is irrational, in a proof by contradiction, you assume not Q, right? So you assume that Q is not true, i.e., you assume that the square root of 2 is rational, okay? And once you assume this, now you reason through a sequence of steps to arrive to a contradiction. Okay, that's the whole purpose of this, is that you want to arrive to a contradiction so that you know that what you initially assumed was incorrect, and in fact, P is true. And so there's several ways of deriving a contradiction and proof by contradiction. One way is just a refutation of what you initially assumed. So if it's clearly if it's clear through this sequence of steps that actually Q is something in your reasoning allowed Q to be true, then you must have a contradiction, right? So if you're refuting your own assumption, or the more general case and the more common case is if you refute something that you already know is true. So for instance, if you refute the premise, or if you refute something that you've already proved before or that you know is true. So for instance, if you arrive at a contradiction, if you arrive at some point that tells you that 0 is equal to 1, let's say, then you know that that's not true, so that's a contradiction, okay? And just an extra note, for notation purposes, whenever I arrive at a contradiction, the symbol that I use, so my personal symbol, which was actually inspired by another YouTube video. So my symbol and this other person's symbol for contradiction is just an X with 4 dots. I just think it's a cool symbol that shows that you've arrived at a contradiction. Okay? Okay, so that's the idea. How do you actually apply this in practice? To do this, I've not chosen the classic square root of 2 is irrational because I know that many of you have already seen this in a discrete math course. Instead, I'm going to do a graph theory proof, specifically a tree proof. So in this example, what I'm claiming is that if I have a tree T, which is represented by vertices and edges, formally by a tuple of vertices and edges. So if I have this tree and I take any two vertices, call them U and V, from the set of vertices in my tree, then there exists a unique path between them. Okay, so before we even get started with the proof, one thing that's always good to do is just make sure that you understand the grounds of the premise. So what's the kind of what are the tools and what are the assumptions you're already working with? So you know that you're working with a tree, right? So let's see, let's just draw a tree here. This is a tree, right? This is a tree. And what I'm saying is, if I have any two vertices, so let's pick two vertices, let's say U, so this is U and this is V, then the claim here is that there is a unique path. So there is a unique path between U and V. Okay, so is this true in my example here, right? I mean, if it's not true already here, then we have a problem. Well, if I go from U to V here, there's clearly only one path to do so, right? So I go here, 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 and here. I can't do something like I go here, here, down, back up, then like this, because that's not a path, right? I'm repeating edges. So the claim is about a path and not a walk. Okay. So so this appears to be true in this case. So maybe what's the intuition here? Well, what do I know about a tree? I know that a tree is connected. So of course, um, this isn't going to be vacuously true because I know that um, because a tree is connected, there's going to be at least a path, right? There's going to be at least a path from U to V. Now, can there be more than one path, right? So is this path non-unique? Well, um, if I pick any two other vertices, it doesn't seem like there could be more than two paths, right? So like for this one here, I can only go here. For these two here, I can only go straight. Um, and so maybe suppose that there were two paths, right? So suppose that there was a path, let's say, from U to V. There was potentially another yellow path, let's say, I don't know, there's a path like this. So this was another path. Well, now we have a problem, right? Because, okay, so now I have, let's say, this is P1. Sorry about the yellow. And this is, let's say, this is P2, right? So I have two paths. Now I have a problem, right? Because I have a cycle. So you can see that the cycle that I've created starts at U, goes through V, and back to U, right? So that's a problem because I know that I'm dealing with a tree. I know that trees are acyclic. And so that would be a contradiction, right? That I would have a cycle in my tree. Okay, well, here I created a separate path, right? So maybe there exists a tree. I don't know what it would look like, but maybe there exists a tree where, you start at U. Um, Maybe I don't have to create an additional artificial path outside of the tree. Maybe everything's contained in the tree. But what happens is I have my path, and then maybe I happen to find a vertex, an intermediate vertex. Let's call it I don't know. Let's call it X, and then uh, I keep going, right? So I have instead of having two distinct disjoint paths, maybe I have two paths that only cross at most one. So I have this path. So let's say that this is P1, and then maybe this is P2, right? So this is P2. Well, that's also no good, right? Because if I take this vertex here, I can see that I've created a cycle that either starts at X or at U, because I can go from U to X back to U. And that's also a contradiction, right? Because again, a tree is acyclic. So it doesn't seem like this is um, false, right? And in both cases that I've shown, um, this is the case because I've arrived at contradictions that produce a cycle in my tree, which I know can't happen because a tree, by definition, has no cycles in it. Okay, so I think that's kind of the idea that I'm going to use to prove this. So this is going to be more of a sketch because I don't want to get all rigorous and formal with notation. But this is going to be more of a sketch. Um, but I encourage you to sort of fill in the gaps where um, you think that things should be more formal and more rigorous. And by more rigorous, I just mean making absolutely clear everything that you're sort of writing down. So if you say, suppose I have a path, then write down what that path could look like, right? So starting at some vertex and then at another vertex. Okay, but for the sake of this video, I'm just going to keep it at a proof sketch. So the first thing I need to do is I'm going to assume, so assume for the for the purpose of deriving, okay, just purpose of deriving a contradiction that there exists, right, that there exists a tree T such that two distinct paths exist between, let's say, some arbitrary vertices u and v. Okay, so my tree here is comma e. Okay, so I assume for the purpose of deriving a contradiction that, in fact, there is a tree T. So a tree T, which I write formally as the tuple v comma e, right? So a set of vertices, set of edges, such that two distinct paths exist between some vertices u and v. Okay, so I've just picked u and v arbitrarily. I know that they're in a set of vertices. Okay, then what happens? So then, in fact, there are two possibilities, right? Then, okay, we have two possible cases. Okay, so two possible cases arise. Either one, so either in the first case, the path, so paths P1 and P2 from U to V are completely disjoint. So completely disjoint, meaning that they don't share, so meaning that they do not share any common, so they do not share any vertices. Saying common would be redundant, so they do not share any vertices other than U and V. So that's actually this case, right? That's actually this case. Okay? So then in that case, so in the case where P1 and P2 are completely disjoint, so in this case, I guess this is actually a bit more formal than what I want it to be, but in this case, what? So, I have U, and I have, let's say, P1 to V, and then I have U, P2 to V, okay? And so in this case, there exists a cycle in my tree T, so in T, where the cycle is, you start at U, you use P1, then you go to V, then you use P2, then you go back to U, okay? So there exists a cycle in T, and this, of course, is a contradiction, right? This is a contradiction because, okay, I can't write down the last dot, but because a tree I know is acyclic, so there cannot be a cycle in my tree, okay? So that's the first case. For the second case, I think I'll try to add a page. Okay, I don't want to put it there. Oh, no, okay, I did. Okay. So, I'd rather it not be horizontal. Okay, whatever. Okay, so, right, so that's the first case, right? The first case is the path P1 and P2 are completely disjoint. The other case is, so case 2 is P1 and P2 have at least one vertex in common. Okay, so this is actually this case, right? So there's at least one vertex in common. So what I'm going to do is I'm going to find a cycle in these two sets of distinct paths. So what I'm going to do is, okay, so I know that I have P1 and P2. They have at least one vertex in common. So now pick the earliest, so quote unquote, earliest vertex in common. Okay, so I know that there's at least one, so I know that there's an earliest vertex. Earliest as in it's the first one that I see in my path, starting at U and ending at V. Okay, and suppose I call this earliest vertex X, right? So then what's happening here is that I have U, then I have my path P1, then I have X. Then maybe I go back and cross again. I don't want to do that. Maybe I go back and cross again with P2, or maybe I don't, and I go all the way to V, right? So I'm accounting for both possibilities, right? So this is P1, and then this is P2. So maybe I cross again, or maybe I go to V, right? But in either cases, if I pick the earliest vertex in common, right, then T has the cycle. Okay, so T has the cycle, and so if I'm going to name this, I'm going to name this subpath P, let's say U to X, and then I'm going to name this subpath P, let's say X to U, right? Then T has the cycle U to X, X. So this is I'm just sort of writing a more compact notation of the sequence of edges. So that's what I meant by this is more of a sketch. So I guess this could be a bit more rigorous. I could have much more proper notation. Okay, and then from X, I use the subpath of P2, and then I go back to U. So T has this cycle, which is a contradiction because I know that T is acyclic, so it cannot have a cycle. Okay, so therefore, right? So I've shown I have both cases. So a proof is also just like it has to be in some sense a grammatically correct and semantically correct set of paragraphs. So there must be a conclusion at some point, right? So I initially started this kind of very loose paragraph with then we have two possible cases. I showed what happens in case one. I showed what happens in case two. And so therefore, because in cases one and two, we arrive at a contradiction, our initial assumption must have been false. So our initial assumption was false, right? So therefore, there does not exist a tree T. So there does not exist a tree T such that T has two distinct paths for some arbitrary vertices, for some vertices U, V in the set of vertices. Okay, so there is no such tree, and so that implies that for every tree T, there exists a unique path between U and V for any, right? For any U, V in the set of vertices. Okay, and that concludes my proof sketch. Okay, so you'll notice that here the crux of the proof was just initially noticing this pattern, noticing that if I suppose not, right? So if I suppose that there are at least two paths that are distinct between some two vertices U and V, Then I have, I have cycles, and actually there's two possible ways of getting a cycle. But then in both, right, in these both scenarios, that leads to a contradiction because it means that the tree, the object that I initially assumed was a tree, wasn't in fact a tree. But that's a contradiction because I assumed that it was, right? And so because of those two contradictions, there can't there there can't have been um, two distinct paths. So in other words, there must have just been one unique path. And because U and V were arbitrary, then now I can claim this for every vertex. And also because T was arbitrary, the tree was arbitrary, I can claim this for all trees. And so that's how I can conclude my proof. Excellent. So in the next video, we'll be talking about another very important proof technique, the proof by induction.